HVAC 360, episode number 65, Radiant Cooling. Hey, welcome back, everybody, to another episode of HVAC 360. I am your host, Matt Nelson. This week, we're going to be talking about radiant cooling. Depending on where you are in the world, you might be a little bit more familiar with radiant heating than radiant cooling, but it kind of acts the same. This week, we got a special guest for you. He's a distinguished lecturer with H3, but let's see, Devin Abellon, got that name. And he works for Uponor, but he works a lot with H3 and their radiant cooling technical subcommittee or technical committee for radiant cooling. So he's a really great resource, and I hope you learn a lot from him. But before we cut to the episode, I'd like to have and thank our sponsor, who is the Building Commissioning Association. If you're involved in the building commissioning at all, obviously the Building Commissioning Association is the place to be. If you want, actually this week is going to be their national conference, May 6th through the 8th. So if you are listening to this after the fact, you got to wait till next year. So get your plans, get it on your schedule already, and mark that out. So with that, we have also a couple of things. Their spring webinar series is also taking place. They got two left, so you can catch either one of these. The first one coming up on May 15th is going to be, is controls, loop tuning, and night setback really that hard? With June 19th being commissioning of grounding system for mission-critical facilities. So if either of those are topics that align with what you're doing, you can go to their website, bcxa.org, that's bcxa.org, and find out more about them. Or even if you just want to join BCA, that is available, and more information is there on the website for you to do that as well. All right. Thanks again to the BCA for sponsoring HVAC 360. And with that, we will cut to the tape with Devin Abellon. All right. We're here with Devin Abellon, who is the Business Development Manager for Commercial Sales for Uponor. How you doing, Devin?
Great.
Hey, thanks for being on here. So I guess let me just start off. I always like to find out a little bit about who we're talking to. So why don't you tell me a little bit about your background?
Okay, sure. I'm a graduate engineer. Got my bachelor's degree in mechanical engineering from UC Santa Barbara. Started my career as a consulting engineer in Phoenix, first at Peterson Associates and then over to LSW Engineers. And I ended up moving over to San Diego, where I managed their California operations for a number of years, really with a focus on high-efficiency system design. So one thing, when I was in Phoenix, I had the opportunity. I worked with this young, bright engineer by the name of Julius Atkins, and he ended up leaving consulting. He went back east, joined a manufacturer, and he was promoting radiant cooling. And this is probably 12, 13 years ago, and I remember he'd call me up and he'd ask, hey, what kind of projects are you working on? I think radiant cooling would be a great application here. And sort of as a conservative, somewhat gun-shy engineer, I'd push back with objections, my reservations, talking about things like condensation, controllability, but he kept at it over time, really became a believer in radiant cooling. He did a lot of research, read a lot of the case studies. I thought, this actually is pretty neat. This really works. And so about 4 years ago, we were talking, and at that time, I kind of decided to make a career change. That's when I joined Uponor, manufacturer he was working for at the time, and now I've got this opportunity. I work very closely with engineers, with building owners, with contractors throughout the country on really some of these some really amazing projects incorporating radiant cooling as part of an energy efficient design strategy.
Yeah, I mean, I got to imagine that your standard run of the mill job isn't using radiant cooling, but so you probably see some pretty neat stuff out there.
Yeah. Typically, projects where they're really focusing on high efficiency. Kind of thinking out of the box and where they've got challenges such as, high solar gain, things that would be very difficult to deal with a more conventional airside system. So, it's not your kind of run-of-the-mill, we're not slapping rooftop units on the roof all over the place. It becomes a very creative, a very exciting and rewarding process.
Now, I mean, if somebody's not familiar with radiant cooling, the term radiant cooling, how would you explain that to them?
Well, one of the things I often use, I use an example of a cave, and again, assuming that most people have been in a cave before, or maybe not a cave, maybe like a large stone building, a large cathedral, if you will. Mm-hmm. And you can imagine maybe it's a warm day, the air temperature is high, but as we move towards the mouth of that cave, as we move into the building, into the cathedral, we feel much cooler. Even though the air temperature may still be high, we feel cooler, and that's because of all that thermal mass. That mass is actually drawing energy away from our bodies, and that's really kind of the basis of radiant cooling. We've got a system where we're actively controlling the surface temperatures of the mass around us within this occupied space, and then we're driving heat transfer in one direction or the other to maintain this comfortable environment.
Now, I guess most people, when they deal with radiant technology, at least from around here in Ohio, they're mostly dealing with it from the angle of the radiant heating. Now,
sure.
Can you talk a little bit about how those two contrast?
Well, they're actually very similar. I mean, obviously, the main difference is with the hydronic radiant heating system, we're circulating warm water, creating this warm surface and then radiating heat. Whereas with a radiant cooling system, we're circulating chilled water through the same series of tubes and creating this cooled surface and then absorbing heat. When it comes to the construction details, they're essentially the same. Some of the differences may be your typical on-center spacing for cooling. Maybe 6 to 9 inch on center for the tubing, whereas with heating it may be 9 to 12 inch on center. There are some there's performance differences, and then also kind of your operational parameters. The other thing to note, I guess one of the key things with radiant cooling versus radiant heating is you do have to be aware of dew point, so we can make sure that we avoid condensation.
Mm-hmm. And obviously, I think that you're like you said in the beginning, moisture is one of those things that is the big gorilla in the room that people need to.
No one ever brings that
up. So I guess let's talk about moisture in
Sure.
in the air. What can you just kind of give us a kind of a back
Sure.
to basic kind of overview of the moisture?
Sure. And, I'll tell you, I was joking, but it comes up quite a bit. It's probably, one of the first things that comes up when people bring up radiant cooling is, what about condensation? How are we going to deal with condensation? Because obviously, that we don't want condensation. We get wet floors. People are slipping. You can run into mold issues with carpet. You can run into wood damage on wood floors. So we need to make sure that the system is designed such that we don't get condensation. But you really have to, kind of take a few steps back and ask yourself, when would condensation occur? And condensation is going to occur when the surface temperature drops below the dew point. So if you take a look, not even with radiant cooling per se, but when you look at your total design for the built environment, you're looking at a number of other factors. And as you look at ASHRAE Standard 55 for the thermal environmental conditions for human occupancy, you're trying to design a space where, let's talk in terms of relative humidity, you're trying to manage the space between 30 to 60% relative humidity, depending on your temperature. That may relate on the high end to a dew point on the order of, 56, 58, maybe 60 degrees. And then you look at that same document, ASHRAE 55, where it's going to tell you that your floor surface temperature, you never want that to be colder than about 66, 68 degrees, just because people will feel uncomfortable if they're walking on a cold floor. Mm-hmm. And so if you look at really how you're designing the entire system, you see right away that a properly designed radiant cooling system that's operating properly, you're never going to even come close to what that dew point temperature is. We've seen, certainly issues in the past where radiant cooling systems have caused condensation. A lot of that had to do with, maybe there were older systems where we either didn't have the understanding of how to control for moisture or just didn't have the right controls in place. And so now we're really seeing that issue. I don't want to say go away, but it's really not becoming much of an issue at all because the systems are being designed properly and they're controlled properly.
Now, I mean, I guess so. In essence, when you take a look at the building, your goal with the radiant cooling system is not moisture control per se. That's going to be
absolutely not. That's true.
That's going to be handled by a completely separate system, usually like a dedicated outside air system.
Yes. Yeah, and you look at some of the studies that have been done. Lawrence Berkeley National Labs, the Pacific Northwest National Lab studies. They all, when we talk about radiant cooling as a system, it's commonly coupled with, as you mentioned, dedicated outside air systems, because a radiant cooling system is only going to address sensible load. So you're going to need a secondary system. You're always going to need a secondary system to provide Dakota-required ventilation. But now this secondary system, a dedicated outside air, does a very nice job at kind of decoupling the ventilation from the sensible load, and then it gives you that moisture control as well for the latent loads.
Now, I guess what are some of the getting more into the design side? I guess what are some of the good applications for this technology?
The capacity of the system is going to be based on surface area. Whatever surface area you have, that's going to give you your capacity. And so, certainly, when we start looking at large open areas, large lobbies, Bangkok Airport in Thailand comes to mind as a good example. Pier 15 Exploratorium, it's a large museum in San Francisco, actually just opened a couple of weeks ago. Those are good examples because they're large open areas that they're relatively easy to manage. But having said that, we're actually seeing the biggest growth in radiant cooling in schools and offices. Manitoba Hydro Place in Winnipeg, that's a great example. NREL's Research Support Facility, which I think you featured in one of your podcasts last year with Paul Torsolini. Mm-hmm. Yeah, and so that's another example, an office application. We're continuing to see this trend in high performance, net zero sustainable buildings where they're targeting these high levels of LEED, gold, platinum, and engineers are looking at radiant cooling as part of that energy efficient design solution. So we're really seeing it, in that right now more than in other areas.
No, I guess what makes it? I'm just curious. What makes it so energy efficient? I mean.
Well, it's the fact that what we're able to do is we're taking care of sensible load basically by using water. We're essentially moving water rather than moving air, and because the heat transfer capacity of water is so much greater than that of air, we're able to basically drive that heat transfer with essentially small circulators, small horsepower pumps rather than large horsepower fan motors. That's one of the key benefits. There are other benefits in terms of being able to manage the comfort within a space at higher or lower set points and other things like that really lend to that energy efficiency.
Now, I mean, obviously, this is not necessarily a magic bullet. What kind of what areas are bad for what doesn't make a good application for this?
Okay. If you're in an area, and we talked about condensation mm-hmm. and humidity, and I actually alluded to a project at Bangkok Airport, which is in a very humid environment. But if you are in a humid environment where you're not in a position where you could actively manage and control the indoor relative humidity within the space, then what happens is you're really forced to limit yourself in order to avoid condensation. So, say you're designing a project, Miami, for instance, and you know that the envelope's really not going to be very tight, then radiant cooling is probably not going to be a very good application there. If you've got a project, a building that has very high load densities, very high sensible load densities, let's say something like a data center, will radiant cooling work? Yes, it will work, but the percentage of load that it's able to offset versus the supplemental airside system that's going to be required is probably going to be relatively small. Mm-hmm. So it may not make too much sense. And then thirdly, I think of buildings, maybe retail pads where they anticipate a high level of turnover. When you've got an in-slab radiant system, you've got tubing embedded into that slab, and so really doesn't give you much opportunity to react to a high level of tenant improvements or reworks. There are instances, there are ways you can work around that, but again, it's probably, if you're anticipating a high level of turnover, it may not be the best fit.
Mm-hmm. So, I mean, obviously systems that, buildings that are going to stay relatively consistent that may be, slated for, being around for 50 or 100 years, that's more the...
Yes, exactly.
So, I mean,
exactly.
Now, I guess you talked about being in the slab. Is that the primary kind of installation that you see is kind of under slab tubing, or what kind of different options are out there for radiant cooling?
There are other options. We see the in-slab, and the slab can be installed either as a floor slab or even as a ceiling slab. But there are other options. There are radiant ceiling panels that are available. It's a great application there. Very quick response. Tend to have higher cost per square foot, but it is very good for retrofit applications or ceiling applications where perhaps the architect doesn't want to see an exposed deck. So there are kind of some pros and cons between both of the systems. The in-slab systems we see have more, there's more interest in them because you're able to take care of kind of that flywheel effect that you get with that large thermal mass.
Now, are most of the slabs that you see exposed, like you're kind of referencing?
Most of them are. The one thing to note, actually that's one thing I forgot to mention when we were talking about applications where radiant cooling doesn't make sense. Mm-hmm. If you've got an installation where they anticipate having, maybe thick carpet, then any type of floor covering is going to have an R value associated with it. It's going to diminish that radiant effect, and so. In most cases, yes, we see either bare concrete, certainly tile or terrazzo. Mm-hmm. Those finishes still have very conductive and very work very well with radiant systems. When it comes to ceilings, either bare concrete deck or bare metal deck is usually what we see. Don't see if you were to put again if the architect wants to have acoustic ceiling tiles, that's really going to, it's not only going to have, the R value associated with it, but then you're also going to have that air barrier as well. So, in most cases, it's a bare, hard surface.
Now, I guess what sort of components are you talking about when you say, okay, obviously we get the tubing, so what other products go along with the radiant cooling system? Well,
there's the tubing itself. And
which is going to be a plastic, correct? Yeah,
you look historically, radiant heating systems were done in copper, but now the industry has really gone towards the cross-linked polyethylene or PEX, and mm-hmm. there are different types of PEX, PEX A, B, and C. But the one thing that's really important is that when the engineer specifies it, they specify it with an oxygen diffusion barrier. So that's one of the key things as far as the PEX goes when we've got a closed-loop radiant system. In terms of other components, the tubing would come out of the slab and connect into to manifolds. And there are a lot of different options when it comes to the manifolds. There are metallic options. Brass and stainless steel are very common in the industry. We are seeing the industry look more towards engineered polymer offerings as well. And there's this notion, I think, among engineers that metal is better than plastic. But as we start looking at the performance, the temperature, pressure ratings, the cost, the engineered polymer options become very viable alternatives. The benefit for a radiant cooling system, of course, is the fact that with a lower conductivity, that polymer manifold is going to be less susceptible to sweating.
Gotcha. Now, go ahead.
Sorry. No, and then, we talked about the tubing, the manifolds, and then one of the key components, of course, is going to be the controls. And a lot of times people, they may shy away from radiant, especially radiant cooling, thinking that controls can be overly complex. But in reality, it's relatively straightforward. I think, one can make the argument that, with any type of system, especially in a high-performance building application, you really want to make sure you've got the controls dialed in properly. If it's not controlled properly, obviously it's not going to perform to neither the engineers nor the owner's expectations. So controls are very important part of that equation as well.
No, I mean, as far as I'm just kind of thinking off the top of my head here, if you had a scenario where you had an existing, floor slab and you covered it with radiant, is there a lot of flexibility as far as, if you needed more or less cooling? Obviously the engineers' calculations only go so far. So
sure.
Is there a lot of flexibility there as far as flow goes? Or, I mean, is that primarily how it's handled?
Yeah, there is some flexibility. I mean, certainly from the design perspective, as you look at your on-center spacing, that's going to have a lot to do with what kind of capacity you're able to run. Also, the diameter of the tubing that you're running. Commonly in commercial applications, you see anywhere from 1/2 inch to 5/8 inch to 3/4 inch diameter tubing. Those are certainly things that you can't change after the fact. Mm-hmm. So aside from that, what you'd be able to change is you can drop the temperature of the supply water that you're circulating through there, as long as obviously you want to be careful with your so you don't run into condensation issues, and you can increase flow. Recognizing that you may run into instances now where you possibly have to upsize the pump because of the pressure loss through the tubing.
Gotcha. Now, I mean, and I guess from my standpoint, sizing, laying out the tubing, is that something that typically you help with?
Oh, absolutely. Yeah, and that's something. As an engineer laying out a system, we provide a lot of support in terms of zoning, locating manifolds, and sizing, sizing the loops. I think a lot of times, though, engineers kind of get caught up in what I call kind of the squiggly lines. If you've seen a radiant loop layout on a set of plans, it's a rather complex kind of zigzag back and forth pattern on the tubing. And a lot of times the engineers, when they're putting together the construction documents, they get kind of hung up on making sure that those are exactly right. And what we're seeing more and more of, though, is that engineers kind of going away from that. As much as we'd like to ignore the fact, contractors, typically they're not going to install based, strictly off of construction documents. They're going to be installing off of shop drawings.
Right.
And so what's usually best, because it is rather time-consuming to draw those squiggly lines, is that we see engineers where they'll take their plans and kind of dash out radiant zones and then have a corresponding manifold schedule that gives it kind of a performance-based approach to how to design that system, and then leaving it up to the contractor and the manufacturer to come up with the actual shop drawings. We found that's becomes it's a much easier for the engineer. They don't have to worry about drawing all those lines and making sure all the loop lengths are equal, and it just helps the process along.
Now, as far as laying things out and the different components, obviously, I would think that insulation to actually promote the radiant cooling effect, kind of going in the right direction, has to be a part of it. Is that true?
Yeah, I mean, insulation is important. Certainly for slab-on-grade installations, you'd want to have your edge insulation, sometimes perimeter insulation. Ground conditions are often very difficult to predict, especially if you're close to the water table. When it comes to suspended slabs, insulation is important in order to make sure that we're driving the heat transfer in the right direction. Having said that, though, one of the common strategies, and this is more common in Europe, is to take what's called a TABS approach, or a thermal activated building system approach, where you're actually installing the slabs with no insulation. And we see some of that. We've seen some of that. In the United States, David Brower Center, for instance, comes to mind, where there's no insulation, there's no thermal break between, the first or second floor. And so what you're essentially doing is you're creating a slab, this thermal mass, where you're driving the temperature, so you're in cooling, and it acts as a radiant ceiling on one floor, and then potentially a radiant floor on the floor above. Now, you may, one of the first objections you hear is, well, now you're losing kind of that floor-to-floor controllability.
Mm-hmm.
You're unable to zone on a floor-by-floor basis. But the idea is that if you've got a typical office building, and let's say it's a multi-story office building, as long as all the functions within that building are relatively the same, if the building's going to be in cooling, all the floors are going to be in cooling. And so you see that approach. It's actually fairly common in Europe, where they're actually taking advantage of that entire thermal mass and really cooling the building as a whole, rather than doing it each floor zone by zone. So in that case, they actually don't have the insulation in there.
Okay, gotcha. Now, I guess what are some of the other common things that you see going wrong with engineers laying out the system? I mean, where are the trouble spots?
Well, I think a lot of the common issues that come up really have to do with just the industry as a whole, kind of the lack, I don't want to say lack of familiarity, but we just don't have as much experience as we do with the more conventional airside systems. And so there are certainly some best practices that are available, number of resources that are available that can help engineers, kind of guide them in the right direction. Certainly support from manufacturers that's available as well. But some of the common problems we see is, first off, not really being able to quantify or understand what the operating conditions need to be in order to satisfy a certain load. We talk about what you can expect from a radiant cooling system, and we'll talk, let's say a floor application with bare concrete. You may be looking at 12 to 14 BTU per square foot, and that's really driven by the minimum surface temperature that ASHRAE recommends. Sometimes an engineer will say, well, I need more than that, and so that they'll specify 20, 30 BTU per square foot, and then all of a sudden, we're running into a condition where the water temps are too low. We could run into surface condensation issues. The floor temperature could get uncomfortably cold, things like that. And so those are just some of the issues that sometimes come up. It's just really more of just a lack of understanding on how the system should be laid out.
Mm-hmm. Now, getting back to the controls of these systems, is it just simply like a control valve kind of situation where you're just modulating the temperature based on a thermostat, or how are they typically controlled?
Yeah, there are a couple of different ways to do it. Most of the radiant cooling systems, and many of the radiant cooling systems that we see are actually combination heating cooling systems. So you're using the same series of tubes both for heating and cooling, and so it gets that adds a little bit of complexity to it. So you're right. Essentially we've got a thermostat, a room temperature sensor that's monitoring how far we are from set point. Typically, we'll have a slab temperature sensor, so we can monitor what the slab temp is. Usually, that's used for high-low limit control, so the slab doesn't get too hot or too cold. And then we're basically, as we're calculating indoor relative humidity, or monitoring indoor relative humidity, we're calculating dew point, and really what the control system is trying to do is it's trying to optimize the system so that it's supplying the right supply water temperature to maximize the effectiveness of that slab while ensuring that we don't get too cold, we don't cause surface condensation. So it's typically, it's sometimes it sounds a little complex, but at the end of the day, it's a number of temperature sensors, indoor relative humidity sensor, and slab sensor all working together to manage that slab. Okay.
Now, I guess I have to ask the question: if you have all those different components, is it a single controller from the controls contractor that's kind of figuring these things out, or is all those sensors separately going back to a building automation system typically, or do you have some sort of special component that integrates the couple different pieces and then sends it back?
There have been some developments within the industry, to have this sort of single point connection for the radiant system, but the most of the systems we see are all handled, just as you had mentioned, through the EMCS contractor, looking at each of the different points, monitoring each of the points separately, and then bring that all back to the front end.
Okay, right. Now, going to the construction side of things, how well? I mean, what's your take on how well the contractors are handling this?
Well, it varies quite a bit from region to region. I mean, obviously, like where you're at, we've got cold weather. Where radiant heating is much more prevalent, the contractors do have a good understanding of how to install the systems, what they need to do in order to get it laid out properly. Warmer climates, where radiant heating really, is not used, we've got there are a number of contractors who have become much more proficient at installing it. What we're seeing is as the number of projects, grow, as we're seeing more and more radiant cooling installations go in, more and more contractors are getting that experience, and it's continuing to improve. But certainly, that's one of the issues when it comes to cost, and that we haven't really touched on cost, but the big kind of variable when you start looking at the cost of a radiant system is going to be in that labor. And when you've got contractors, in certain areas where they just don't have that familiarity, that level of familiarity with how to install the systems, certainly they're going to protect themselves and have their labor covered. And that's why we see some of the great variances in pricing. So I guess, would I say that it's the level of competency within contractors throughout the country is high? Probably not very high, but it continues to improve.
And I guess what sort of training is available for them if they were interested in learning more about this? I mean, is this kind of hey, you know how to lay this tubing and you take you just learn by trial and error, or are there some sort of preparatory classes that a contractor could send a couple of guys to figure this out?
Yeah, there are a number of training opportunities out there. RPA, the Radiant Professionals Alliance, they have training. Most of the training is done through manufacturers. We have a training facility in Apple Valley, Minnesota. Do a lot of factory training then, and do a lot of on-site training as well. What we see a lot of, especially with contractors who haven't installed or don't have a lot of experience installing, is kind of a pre-construction training where all the contractors get certified. They understand the system. It's important. At the end of the day, it's not a very difficult system to install, but certainly they need to be aware of what what the proper procedures are, so that it's done correctly.
Now you mentioned certifications. What I mean is obviously from the engineer's standpoint, one of the things that they'd want to put in specifications, if it existed, is any sort of certifications or requirements. Is that more of the I guess, one, do they exist, and two, is it more of a from the Radiant Professionals Association or from manufacturers? That which way is more typical?
It's really there isn't much in terms of industry, kind of an industry-wide certification. It's really more of It's at the manufacturer level. So you're right. We'll typically see specifications that call out for manufacturer-approved certification, and many of the manufacturers do offer that.
Now, I mean, as far as a manufacturer goes, is it, obviously with certain systems, there's a lot of, if you're talking about a roofing system or possibly a wall system, there's site inspections that manufacturers do. Is that something that is the same with these type of systems?
It is, yeah. And that's, I can't speak for what other manufacturers do, but it is very common. Certainly, it's important that the installation is done in accordance with both the specifications and the manufacturer's recommendations. And so it's very common to have kind of on-site review, and that we commonly see that as a requirement in the specifications.
Now, I guess just give me a flavor. What are some of the things that the contractors might miss when they're installing these types of systems?
Well, one thing to note is, with the different types of products that are available, there are different types of fitting systems that are out there. So it's important that the contractor understands how to to make the fittings properly. Other things they need to make sure that they understand how to lay the tubing out and how to secure it. There are a lot of different options as far as securing tubing into the slab, be it with, we've seen wire ties, zip ties, staples, rails, there are knob mats, groove mats. There are a lot of different ways to do it. So the contractor just needs to understand how, based on the requirements, based on the specifications, how that particular project needs to be installed.
Now, you mentioned the like the groove mats and things like that.
Uh-huh.
I got to admit, usually when you hear about radiant, whether it's heating or cooling, it's like, oh yeah, there's the tubing, but you know what? We got this really neat time saving device, and I guess really that's what they are. These, when you use like a groove mat or some sort of system like that, that's a time saving device for the contractors to help them and getting it laid out quickly.
Exactly. Yeah, because at the end of the day, you're looking at tubing that's embedded into the concrete, and there are a lot of, I guess we'll call them just kind of means and methods in terms of how to secure the tubing, and a lot of contractors will go with that that type of solution in order to help manage their labor.
Now, is there any other, if there's contractors listening, if there's any other best practices that contractors can kind of follow?
Well, one thing that we always strongly recommend is that on any project that they have a pre-construction coordination meeting. A lot of things go into a slab. We've got the radiant tubing in there, but we also have there's rebar. There are other supports. Many times we've got conduit. Maybe other electrical boxes and things. Mm-hmm. So it's important that as far as best practices go, make sure that we understand exactly what's going in the slab, who's going to go where, review the shop drawings, know exactly, what the layout's going to look like, and that you've got the right materials and everything on hand in order to lay that out. One thing one thing to know with PEX in general is PEX is a very durable material. And so, they lay it out onto the slab, and the contractors walk all over it all day. It's very durable. But at the same time, if you've got other trades in there, if they're welding around it, if for any instance they get any type of puncture in the tubing, that's obviously something that would need to be repaired. And so one thing that you always want to make sure you do prior to pouring the slab is to pressure test the system.
And do you do that typically with a water pressure test or an air test?
It can be done with either.
Now, if you determine that there's a leak and you find the leak, is it kind of can you replace it? Is there some sort of like heat welding that goes that takes place, or do you have to replace the entire circuit?
With a type of when there's a puncture, you can basically cut out the piece of tubing that has the puncture, and then connect a new piece just as a repair. You want to be a little careful. Certainly, best practice is not to have any fittings in that slab, because the thought is that a fitting, if you're going to get a leak anywhere, it more commonly than not, it's going to be at that fitting. Some of the manufacturer recommend that if you do have to install a fitting in the slab, that you wrap it. Obviously, you want to make sure that the fitting itself doesn't react with the concrete, so they're trying to protect that. We use engineered polymer, and that doesn't react with concrete, so they're able to do that without having to wrap.
Yeah, I got to imagine, at least from a kind of a retrofit application and looking ahead, I got to imagine that, kind of like rebar, where they have to X-ray the slab, is kind of knowing exactly where the tubes are. If you're ever going to, drill another hole in that slab, it's got to be critical.
Yeah, you know what? It's that's one of the things that often comes up, and from kind of the owner perspective is, if they've got a we ran into this with the museum over in California. They were trying to install new displays, and they're drilling right into that concrete, and they hit tubing. One of the things that kind of another best practice is we're seeing a lot of building owners, they'll invest in a thermal imager, or contractors do this as well, And depending on where the slab is within the profile of that slab, where the tubing is within the profile of that slab, they can crank up the temperature on that, run hot water through it, and then by using a thermal imager, they're able to visually see where the tubing is.
Oh, it's interesting.
So we see that quite a bit. If they're trying to maybe put one new wall in, they want to kind of know exactly where they can and can't drill down, then that works very well.
So I guess, speaking of the owners, what kind of training is kind of required for these types of systems?
There's not much training. Certainly it's important that, well, let me take that back. It's important that they understand, what the system is and how it works. It's really more a question of managing expectations. There's a project that we were involved with. It was another museum project where they were just convinced that the radiant cooling system didn't work, and went over there to take a look at it, and they said, look, and they went and they flipped the switch, and then they walked over to the slab and said, see, it's not cold. And so, obviously, with a thermal mass, it's going to take time. It's not like your airside system where you move the thermostat and within 2-3 seconds hear the compressor go on and the fans start blowing. It's something that takes time. So as long as we can manage the expectations, they know how the system's supposed to operate, then it ends up being, very, very easy system to manage and maintain.
Now, I mean, one of the things that pops into my head, obviously, with any sort of piping system, is getting debris, getting these circuits clogged. Has that been a real issue? I mean, what sort of precautions are taken to prevent this?
It is an issue, obviously, especially when we're talking about relatively small diameter tubing. You can have half-inch diameter tubing or even smaller in some applications. And then you've got the manifolds, with the series of valves there that are opening and closing. So, yeah, debris is important. I guess, in terms of best practices, you want to look at what you're doing, doing with your hydronic system in general. Making sure you've got the strainers in place, making sure that you're managing the water, so you don't run into that type of issue. The one nice thing with the cross-linked polyethylene versus the metal pipe is it's not something that's going to be subject to any type of corrosion or material buildup over time. It remains relatively clean, throughout its life. So you don't really run into those type of issues. But certainly anything that when it comes to maintenance, really not much you need to do aside from managing your chilled water supply return and your hot water supply return as you normally would for the rest of your system.
Now, are there any sort of chemicals that don't play nice with the cross-linked polyethylene?
There are some. Usually, really, in terms of the chemicals that are used for for your hydronic system, the only one you really want to avoid is ethylene glycol. That could react poorly with the polymer fittings and such within the system. Aside from that, really nothing that's commonly used that would cause any problems.
So what about is the propylene glycol okay then?
Yeah, propylene glycol is fine.
Okay. I guess what kind of feedback do you get from these type of systems?
The feedback we've got has been very positive. The radiant systems themselves, they create very comfortable spaces. The owners are seeing that they recognize, kind of the environment they're able to create for their occupants, and then they're also seeing it in the energy savings. We talked briefly earlier about how they're able to shift that fan motor horsepower over to pump motor horsepower, and so they're able to see both the comfort as well as the energy benefits. And again, as I mentioned previously, once they have the system dialed in, it becomes relatively easy to manage.
Mm-hmm. Any other misconceptions that they haven't already covered?
Misconception. Well, let me throw one thing out there. Is oftentimes when we bring up the idea of radiant cooling, and we talked briefly about it earlier when we were talking about radiant ceiling panels. Many times, folks kind of associate that with chilled beams, and it's important to just differentiate between the two, because chilled beams actually, while they do have a radiant component, rely more heavily on convection. So chill beams, when you talk about radiant, chill beams really isn't considered radiant cooling, although that the two strategies do work very well together. As far as other misconceptions, one thing that we hear quite a bit is, you may go to a building owner, or you may go to an engineer, and they may make the comment that I like the idea of a radiant cooling, but they're just so slow to react. I don't know, you probably heard that. The reason, I guess this isn't really a misconception, because the reality is they are very slow to react. But the misconception is the fact that kind of that aspect of radiant cooling hurts the controllability of the system, when in actuality, you can almost make the argument that a radiant cooling system or radiant heating system, it reacts instantaneously. And the reason you can make that argument is if you've got a slab that's, for instance, managed at say, 70 degrees, if it's 68 degrees in the space, and if you have a 70-degree slab, then you've got heat transfer, warming, radiating, so you're warming. But once the temperature in that space starts to elevate, let's say it's 74 degrees in the space, now that 70-degree slab is in cooling mode. It's absorbing heat. So it does a lot to in terms of being slow to react, you can't, you wouldn't expect a slab to go from 84 degrees to 68 degrees at the touch of a button, but at the same time, it does react accordingly to the space conditions around you instantaneously. So you're able to manage a lot of the fluctuations in the load by managing kind of a moderate temperature within your slab.
I got to imagine it's stabilizing, so to speak.
Exactly. Yeah.
Great. Well, Devin, I appreciate you having you on. Anything else that you'd like to add before we go?
Well, if anyone's interested in learning more about radiant cooling, there just are a ton of great resources out there, either through RPA, through ASHRAE, through many of the manufacturers. We actually just finished our radiant cooling design manual. So there are other resources out there. And if it's okay, if I can give just a quick plug,
I'd
like to encourage everyone to attend. We've got the upcoming 2013 ASHRAE Annual Conference in Denver coming up in June, and I recognize that if you're listening to this afterwards, this doesn't mean much to you. But a lot of great seminars there. Not only with this seminar, certainly the winter and the other future annual conferences as well, but a lot of great seminars on high efficiency design. I've got the privilege of being the program subcommittee chair for ASHRAE TC65, and we've got a program on the fundamentals of radiant cooling system design and construction that Wednesday. So hopefully we'll see a lot of people there at the conference, and thank you very much.
Not a problem. And if anybody's interested, obviously a lot of these sessions are pre-recorded or recorded and are available for purchase at the ASHRAE website. So, all right. Well, Devin, it's great to have you on the show, and I really appreciate you taking the time out for us.
All right. Well, thank you, and thank you for all you do putting together this podcast.
All right, and we're back. Thanks again to our special guest, Devin Abellon, who took the time out of his busy schedule to talk with us. It's great. And Devin is actually a listener to the show, and I really appreciate him listening and promoting as well. So it was great to have him on and talk about something that he's very passionate about, which is radiant cooling. Also, if you want, just like Devin, if you want to pass it on, if you enjoyed this episode, go ahead and pass it on. I'd really appreciate that. If you want, you can actually give us a rating in iTunes if that's how you listen to the show. You can go there and give us a rating. Actually, I had upgraded somebody last time. I had the last episode. We had the subcomandante Mitch. Was the person who actually left me the note. I upgraded him to a commandante, so he's moving up in the world. So I appreciate those kind words, Mitch, that you left for me on the on iTunes. And if anybody else would like to add your comments to him, that would be great. Also, I just like the fact that in the middle of the show, I had my phone ring here. in the studio, and it's just kind of the way it goes here. We're live. We're can't really edit anything out, so that's just the way it is. Hope you enjoyed it. If you missed it, you might want to rewind it and play it again. But yeah, that's I just point that out. If you want to get a hold of me, if you have any show ideas, if you like this, if you didn't like it, you can make comments, show ideas, anything you want. You can find me at matt@buildingx.co. If you want to just sign up for a newsletter that I issue on a monthly basis, that can be had at going to the blog at buildingx.co. Or if you want to interact with me on Twitter, my handle there is @buildingx. All right, and of course, LinkedIn. If you want to connect with me, I love to connect with listeners. I think that's a great thing to do. You can find me, Matt Nelson, PE, on LinkedIn. All right, again, thanks to the BCA, the Building Commissioning Association, for sponsoring the podcast. I really appreciate the support from them. And that's pretty much it for this week. So everybody, get back to work. Thanks for listening. I really appreciate each and every one of you. You make this thing just worth doing. So as always, remember, know what you build and share what you know.